Okay, the last problem we're going to be looking at is sample problem 17.3. Now, this is a classic physics problem, but I think it's a great example of the things that we're doing here and an application of the concepts that we've been looking at. So in this case, we have a sphere, a cylinder, and a hoop, each having the same mass and radius. They're going to be released from rest on an incline. Determine the velocity of each body after it has rolled through a distance corresponding to a change of elevation h. Okay, so I'm going to pull, well, maybe it's on the next page here. There we go. What we're going to do is we're going to look at each one of these, and we're going to just have a generic. Now, remember, they all have the same mass and they all have the same radius, so we can kind of represent them all as we see here. So this first position is starting at the upper portion of the incline. We're going to let it go, and it's going to start rolling down, and then this is going to be position 2. So position 1, position 2. Now, we want to, and I'm gonna kind of show you in the end. We want to know what that final velocity is in terms of the height, okay, that it passes through. And that's that this is this distance right here, this vertical height, okay? So this is what we want to get to. And we're going to start with this illustration right here. We can work it two ways. And I'm going to show you the first way is going to be using the conservation of energy because we haven't used that one yet. So I want to show you that. The second way that we can work this is using work energy theorem, okay? And we end up at the same place, but it just looks slightly different. On the slide, it's kind of funny. On the slide, they have the work energy theorem, and in the actual book example, they do the conservation of energy. So like I said, we're going to work it fully through the conservation of energy, but then I'm going to show you how we can also do the very same thing with the work energy theorem. So I'm going to go back underneath my camera here. And we are going to get started on our problem. Okay, so this is sample 17.3, okay? And what I want to do is I just want to first start out with some of kind of the basic information that we need to keep in mind here. And again, we're going to use the conservation of energy approach, if you would, okay? Sphere, modulus of moment of inertia, it's going to be equal to 2/5 times mass r squared. We did put that on our equation sheet. For a cylinder or a disc, same thing. It's going to be 1/2 mr squared, and that's the radius to, from the center of rotation to the outermost material. And then the hoop, it's just going to be m times r squared, okay? And then we want to find, okay, V2 as a function of h, okay? Now, illustration-wise, I'm going to draw an incline. I'm not going to draw the circles because I know I'm not going to get tangencies. And I know my incline is probably a little bit exaggerated, but I'm going to show the first center of position 1, the higher position, and then the center of position 2. Through each one of those centers, we're going to have the weight of each one of those objects, okay? And we know the mass is going to be the same, okay? And then this difference is going to be our height, okay? So as we look at, for instance, work done, this would be the force through the distance. As we look at potential energy, we're going to find the mass, multiply it by gravity, which is the weight, right? And we're going to then multiply it by the height. So it's another form of gravitational potential energy. Now, additionally, along that incline, it's going to be our point of where it actually is going to touch, and this is going to be, if you would, the friction force, opposing motion. This is going to be the normal force. And then this would be, you know, theta. So again, this is going to be position 1. And this is at rest. So we're just holding, if you would, any one of those, the sphere, the cylinder, or the hoop at the top of the ramp. And then down here is position 2. Okay. So position 1, position 2. Now, again, our approach is going to be conservation of energy. So we're going to take T1 plus gravitational potential energy plus elastic potential energy. That's going to be 0. So we're not dealing with any springs. Then T2 is going to be plus V gravitational plus V elastic 2. Now T1, because we're starting from rest, that's also going to be 0 on the left-hand side. T2, that's when we get down here. That's going to be the second position. Because we are just comparing from our start to this position right here as a function of H, our gravitational potential energy is exhausted. So that's going to go to 0. And so will the elastic. So the only 2 terms that we have to deal with are going to be the gravitational potential energy is going to be equal to the kinetic final at that position number 2. So let's look first at the kinetic energy T2, because that's the one that we're most used to. So T2 is going to be equal to 1/2 mv squared plus 1/2 moments of inertia times W squared. Now, in this case, our W, we know, is equal to V2 over R, okay? Because that's going to be the final velocity when we're down here. So we're going to take 1/2 times mass times velocity 2 squared plus 1/2 times I. But now we're going to expand this out to be V2 squared over R squared by multiplying that out. Now, we don't know what our V is. We don't know what our R is, because remember, we're going to do this as a function of H. So we're going to do some more substituting here. Now, we know that gravitational potential energy is going to be equal to mass times gravity times height. Okay, so we're going to just take this and set it equal to this. So we've got VGR1 is equal to T2. So MGH is going to be equal to 1/2 times take mass plus, because we're going to pull the 1/2 out on either side here. So it's going to be mass plus I over R squared. And then we're going to pull the V2 squared on the other side. So what I did was I factored out the 1/2 and the V2 squared. I put those on either side. And then this is what's left over in the middle. Okay. Does that make sense to everybody? Just take a peek at that and make sure. So I pulled out the 1/2 because that was in both of these. So that would be the 1/2 out front. So then it's going to be M. And then both of them had a V2 squared. So I put that at the end, and it's M plus I over R squared. Make sure you get that down so that you can just kind of understand where that came from, just algebra. Okay. Now, remember, we're trying to find V2, okay, as a function of H. So we want to get V2 by itself, okay? So what I'm going to do is I'm going to multiply 2 up, And I'm gonna take this quantity and put it underneath if you would, right? So that means I'm gonna have 2mgh divided by m plus I over r squared, okay, is equal to V2 squared. Now, I want to try to get my mass to cancel out. So to do that, I want to factor mass out of the bottom. So then the masses can just cancel top to bottom. So to do that, okay, I'm going to go underneath here. I'm going to say 2mgh divided by, now I'm going to pull the m out, and that's going to be a 1 here. And then I'm going to say plus moment of inertia. I had to multiply this second one times m so that I could factor it out. Okay. So you guys remember that from algebra? Now what I can do is I can take these two m's and they cancel out. But this one stays down here. Okay. So I can say that V2 is equal to square root of 2gh divided by 1 plus 1 over, or I'm sorry, moment of inertia over mr squared. All right. So we have V2, if you would, in terms of H. And now what we're going to do is we're going to substitute our values for the moments of inertia so that we can get each one of our V2s for a sphere, a cylinder, and a hoop. So 3 different values in terms of H. So let's look at the sphere first. Okay. We know that for a sphere, I is equal to 2/5 mr squared. Okay. So I'm going to take that equation that I just had, V2 is equal to square root of 2gh on top divided by 1 plus I over mr squared. Okay. Now I'm going to substitute in my value for I to be the 2/5 over mr squared, or 2/5 mr squared. So on top is going to be 2gh divided by 1 plus. Now instead of I'm going to put 2/5 mr squared divided by mr squared. The mr squared cancels top to bottom here. Okay, and I'm left with 1 plus 2/5 in the denominator. Okay. For the sphere, V2 is equal to 0.8452 times the square root of 2gh. So the value that's out here is taking 1 plus 2/5, taking the reciprocal, and then the square root of to get that value. So what I want you to do is make sure that you can, in your calculator, take the reciprocal of 1 and 2/5, get the square root, and you get that number out front. That's your first value. I'm going to give you a little bit of time to plug that all in. Anybody get that number yet?
Is it okay if we multiply the reciprocal by 2, so only gh is in the square root?
I'm sorry, I'm having a hard time hearing you, Megan.
Hold on, I'll put it in the chat.
Okay, thank you. Oh, she's asking if we can take the, oh, the 2 out as well. Yeah, I guess you could. I guess you could. You'll just notice that in the sample, they kind of kept that chunk together. Yeah, I think you could. Yeah, yeah. And then it would be just a G and H. Yeah. All right, now we're going to do that very same thing for the cylinder. So we're going to have V2 is equal to, now I'm not going to redo all of this. I'm just going to put in my numbers. So 2GH divided by 1 plus, and then my I this time is going to be 1/2 MR squared divided by MR squared. So those two guys cancel out, right? And you should get V2 is equal to 0.8165 square root of 2GH. And again, maybe your number differs a little bit if you pull that 2 out. And then the last one is going to be the hoop. Do you guys do this experiment in physics? Or did your instructor show you this? I always did it. I had this very same thing where I had a cylinder, a hoop, and a sphere, and they had the same mass and radius. And then what we did, what I did as an experiment, we calculated moments of inertia and then which one is going to get to the bottom of the incline, fastest. So kind of a little race. We know that I for a hoop is MR squared. We did exactly that. Yeah, it's classic. And that's why I wanted to do this example, because now you can kind of see, it in these terms as well. So V2 is going to be equal to the square root of 2GH divided by 1 plus, and our I this time is going to be MR squared divided by MR squared. So those two cancel. So now it's just going to be the square root of 1. So your V2 should come out to 0.707 times the square root of 2GH. There you go. Now, as I said earlier, this one can actually be solved using the work energy theorem as well. Okay, so I am not going to rework the whole thing just for the sake of time. Oh, wait, could we also do, you could, yeah. Yeah. Yeah, there's a couple different ways. Kelly likes to. No, I'm not even gonna say. Actually, once you said that and you suggested, could we take the 2 out too? It kind of makes sense to do that because that's one of our constants, if you would. And actually, even gravity, because I mean, are we going to be calculating this anywhere other than on Earth? So, so then it would just be a function of the H. So, yeah, I think you could take this steps further, for sure, for sure. Now, I'm not going to redo this problem for you guys, but I wanted to show you the work and how the work energy theorem, I'm sorry, the work energy theorem gets us into the same place as well. So this problem, using the work energy theorem, our T2 remains exactly the same, right? But it's the work part that is different. And in this case, what we do is we take the force times distance and we use the weight times the height, because as we look here, the weight is what's pushing it through that distance. So that's our force times our distance. Okay. So in the work, then, if that's the case, we're going to have our weight times our height as the distance, and then expanding that out, it's equal to mgh, which is potential gravitational energy. Okay. So truly could do it either way. All right. And you'll end up with the very same thing. And then you get here, and then you can, do the rest. So just wanted to show you that sometimes it can be more than one approach that is going to work. All right. So that is sample problem 17.3, which sets you up for, I believe, kind of hitting all the different elements that I wanted to in the practice problems so that you can then have, better luck doing the application problems. So you would be ready then to go to those application problems. The application problems, you're going to notice if we go back to module 3 and we look at our application problems, there's going to be 3 of them that you're going to do from chapter 17. Okay. And like I said, we touched a little bit on every one of the elements that you're going to need there. So for now, I am going to stop the recording and then we'll kind of, take questions.